In this screencast, we're going to learn how to approach a material balance. The most important thing to realize is when balancing steady state systems that mass in always equals mass out. It doesn't matter whether there's a reaction, it doesn't matter if there's more than one phase, doesn't matter the mole fractions of anything, mass in has to equal mass out. Here are some pointers that might be able to help you. The major problem is that students don't know how to take a problem and turn it into a system. So ask yourself, what does the problem ask for? Write it in terms of variables that you set. Read the problem carefully. Ask yourself, what do they want? Look for key words or phrases. If you see something like overhead product, then it means that you have product coming out of the top of perhaps your column. Be careful of what you assume. Some examples of this are adding streams, leaving streams out, and let me show you a typical example. Let's say we have an absorber. There's a gas stream that comes in and comes out, and a pure liquid enters the absorber to absorb some of the components of the gas stream. Well, if this stream enters the system, it needs to exit the system, even if the problem doesn't specifically say that there's an aqueous stream exiting the system. It has to come out, even if it's not pure. In fact, it probably isn't, because the purpose is for it to pick up some of the components from the gas stream. The next thing to do is draw the picture. Label the unknowns and the knowns. What I tend to do is I use M for mass and I use N for moles. For simpler problems, I'll use X for our mass fractions and Y for our mole fractions. If I'm looking for a particular mass fraction or mole fraction, I tend to label it with something that indicates the component. So for example, if I have a mass fraction of benzene, I'll call this X sub B. Finally, if there's more than one stream that has benzene, let's say there's benzene in stream 2 and in stream 4, I'll write X sub B2. The more organized you are, the easier it is for you to solve. Another suggestion is to solve for the easy unknowns ahead of time. Don't do major calculations, because first of all, you may end up confusing yourself, and second of all, somebody looking at your flowchart may not understand how you got a certain number. But things like if you have a 2-component system and it says that it has a mole fraction or 40% benzene and the rest toluene, you can write 0.40 benzene and 0.60 toluene. Now we start with the material balances. And the thing to remember is that there is one mass balance for every component. One thing that you can do is that you can substitute one overall balance for a component balance. And one of the things that you have to be careful of when you are doing your mass balances, that each one of your equations or balances is independent. So let me show you an example. We have two streams that enter a column. Our stream 1 is 30% A and the rest B. There's an example of solving for simple unknowns. Stream 2 is 40% A and the rest C. So two streams exit the column. Stream 3 is 100% A, and stream 4 is 20% B, and the rest A and C. And we're going to write this using the fact that the sum of the mole fractions equals 1, so our x sub c is equal to 0.8 minus x sub a. And we're going to assume that everything is in mass fractions. And so we need to write the mass or material balances. We'll call this M1, M2, M3, and M4. So now let's do these mass balances. And we'll start with A. So the amount of A that comes in is 30% of M1 plus 40% of M2. And exiting, we have 100% of M3, or just M3, plus our x sub a times M4. Now we'll do the B balance. Coming in the first stream, 70% is M1. There's nothing in M2. There's nothing in M3. It's 20% of M4. Now our C balance, which nothing is in M1. C is 60% of M2. And coming out, we have 0.8 minus x sub a times our M4. These are our three component balances. Let's see what happens if we add them all together. So note, when we add them all together, what we get is the overall balance. So we can only use 3 out of these 4 equations to solve our system. Finally, note that we have 1, 2, 3, 4, 5 unknowns, but we only have 3 mass balances that we can write. So as this system is stated, we can't solve it. This is what's called a degree of freedom analysis, and I'd like to direct you to another screencast that describes what a degree of freedom analysis is.